Thank you for coming for the data-centric computing panel discussion. Yeah. Can you?
Slides are over there.
Yeah. Go next. Yeah. Is this the first slide? I don't think so.
Yep, it is.
Okay, then let's move on. So it seems it's not the one, but let's move forward. So in the afternoon, you heard about the various topic related to data-centric computing, and in the past, CPU mostly handling the data processing, but due to the various issue like power efficiency and the performance, people start to introduce different type of processing engine like GPU. We heard about the computational storage and also computational memory and the neural data processing and packet processing, data TPU. A lot of different type of processing unit introduces. But the processing unit try to solve a certain problem, but we have sort of fragmented the market and technology right now. How we can actually connect them together, how can use that together is very challenging. Each technology tries to kind of dominate the market, but we don't believe that the one technology can solve all the problem. So data-centric computing, the workstream, actually try to address this problem and understand actually what is the issue and what would be the right solution to address the problem. Next, please.
The PowerPoint was not the one, right one.
So I'm Yang Seok-ki from Samsung. I'm Vice President of Memory Solutions. And today we have actually honored to kind of invite renowned professors and technical leaders in this domain. Next. Ada, can you briefly introduce yourself?
Sure. I'm Ada Gavrilovska. I'm on the faculty of the School of Computer Science at Georgia Tech. And I'm joining this panel also partially with my hat of a primary investigator in one of the new SRC DARPA centers on processing with intelligent memory and storage.
Okay, thank you. Next, Christos.
Good afternoon, everybody. It's great to be here. I'm Christos Kozyrakis. I'm a professor of WNCS at Stanford University. And I guess I have the interesting background that I've worked on about 15 years on data centers, cloud computing, and so on. Started as a hardware person, became a system software person, and lately I'm doing AI applications. So there's an interesting perspective there and lessons to discuss.
Great.
Hello, my name is Hoshik Kim. I'm VP and Fellow of System Architecture at Memory Systems Research at SK hynix. I'm currently leading pathfinding and research activities regarding computational memory, computational storage, and memory disaggregation in CXL area. So happy to join here.
And I'm Pankaj Mehra. So I'm founder of Elephance Memory. And it's a two-person startup in which we are writing an operating system for emerging memory devices. It's fun to do code again. Previously, I did Samsung Smart SSD together with Dr. Key, and I have history at Tandem, Compaq, HP, and a few startups.
Okay. Thank you for introduction. So since we already heard about application and the technology, in this panel discussion, we may just go into actually the challenges in the the issue we may need to overcome directly. So we sort of pick up some topics in advance. So here you can see the 5 topics. So we're going to go one by one and hear about the technology and the challenge and the issue from each panelist briefly. So the first one is, okay, why we want to move from CPU to the XPU. And the main reason is, okay, we move data unnecessarily. That is data movement issue. So how do you think about that issue and what is the main challenge in that? Pankaj?
Sure. I'd see two principal issues. I think one is, of course, data gravity. Like I mentioned, we want to respect and process data where it is for power and latency reason. But it's not always possible. We have very efficient concentrated compute in the form of GPU. So the second is friction. When we do move data, for example, through CXL tiers, address changes. And if you have graph data or pointers, that is very disruptive, requires swizzling. And so I think some things we'll talk about will help with this kind of thing. But these are principal drivers of why we want to talk about data movement.
Okay.
Yeah.
Hoshik?
Yes, data movement is very important. We can expect a lot of savings in the data movement between storage node to compute node, but the most challenging part is the computational memory part. Computational memory is already very close to the CPU and processor, so the benefiting from those computational memory is more challenging. Besides, except if we can implement some logic processing unit instead of processing memory units. So there's a still challenge in computational memory side.
Okay.
All right, so data movement creates a major energy problem, and there's only two good solutions. The one is to rework your algorithms to generate locality, so you read once, you process multiple times, or to send the computation to the data. Now, both create an interesting issue. You need help from software, either to expose locality or to help you understand what's the association between data and compute, so you can actually do the movement. And I think one of the major themes that is interesting for us to discuss is how do we help programmers expose the knowledge that they have in their application so we can exploit them. If we just try to detect this automatically, given all dusty code, I don't think we can optimize things really well.
Okay.
Actually, I have a little bit of a sort of different perspective. As we look at this complex landscape of different technologies, all of a sudden they expose many different options of where data is and many different paths to data. And so while data movement creates all of the problems, all the challenges that the other panelists mentioned, it may be a really helpful tool, given that alternative paths exist to address different bottlenecks in the system that may be created because your ideal place where you want to process data has a huge queue, for instance. So there may be some opportunities there, given what these future systems could look like, to strategically use data movement.
Okay, that's great. Yeah. So since we're gonna cover 5, let's move on to the next one. So as you saw in the previous presentation, right now people build a device, but actually what we are trying to do is not device solution. Actually, we need to solve the problem from the system perspective. Whether a device provides certain functionality, it needs to contribute overall system. Otherwise, it is kind of the useless, right? So in that perspective, what kind of challenges you see or issue you see in in your research? Ada? Yeah.
So maybe the last example that I gave really plays on this. So this is really an example where by having a system-wide holistic view of your platform, you can take advantage of trade-offs that exist with different decisions on data placement, data processing, data movement, and can achieve kind of better platform-wide efficiency.
Okay.
I totally agree. It's a system problem. Most applications are scale-out applications. There's no application you can think of that can satisfied by a single chip. And there's no single chip that can satisfy all the patterns you see across different applications. So now as you start thinking about making more useful systems, there's some really hard problems to solve there. One of them is, how do you provide devices that can be mixed and matched in different systems, optimized for different corners? Right? If you're going to do some system-level optimization, whether at design time or at runtime, you need to make sure that your device play along. Some devices that are interesting and we spend a lot of time looking at right now, they kind of go the opposite way. Think of a SmartNIC. A SmartNIC is a very opinionated device. You have to center the universe around it. It doesn't play nicely with other devices that have their own personality. But we need to take a step back and think about the intelligence to be in the overall system, not in any individual device.
Yes. Yeah, I also agree that the system, we need a holistic approach to look at the device and system, and to infiltrate the computational device XPUs into existing system, we have to have a software platform and systems design which is backward compatible. And then yes, so if we have to change our system software and platforms significantly to adopt this XPU, there will be a more friction from software side. So yeah, that's the important part, I think.
So very quickly, I think the points are very well made. There are two quick points. One is that a device has a mother-may-I relationship with system today. And as device disaggregates and starts to attach to something that looks like a fabric, it needs to look more like a service. If something happens to application hypervisor or guest OS, the world should not fall apart. If you put memory in there, its permission should not go away. It should be like hardware capability. So the responsibility of device rise and it starts to look like a system as it attaches to a fabric. And I think second point builds upon Christos's point and Ada's point a little bit, and also yours, Hoshik, that I think software maturity is needed which starts to look like systems. So we need rendezvous between function and data that is very flexible. For reasons Ada mentioned, queues can form where you did not expect them to. So a DPU might be a better location to do something which in time of lesser load might have been computational storage or a near CPU acceleration. So I think having that flexibility where data can move freely and rendezvous with compute where it's available at a particular point in the system is really important for big system in which you cannot predetermine everything.
Okay, so I may want to ask questions. So then there are the various activities. Pankaj, in your presentation, you mentioned about the AMD ROCm, Intel One API, OpenCL. But what do you think about that? Did they actually address the problem?
So these APIs were born in a compute-centric view. And the most they can think about is the CPU and the device near it. They're single-rooted for the most part. And there is a disconnect between the real high-performance computing world where we have parallel computed with 10,000 CPUs for 30 years. But somehow, when we enter data center server, that view is getting lost. So I think some learnings need to be combined and some maturity that combines best ideas from everywhere.
Okay.
Yeah.
And the next kind of item and challenge is co-design. It's not challenge actually to solve the problem. We have to see the problem holistically, not from just software perspective and hardware perspective. So what do you think about it, Pankaj?
So actually, Dr. Ki, I might turn question around quickly back to you because you have good view on some of these things. I think more and more we are realizing, and your work in 2013 you published on database, I think since we first built computational storage and recently computational memory, we start to realize that, for example, database optimizer needs to engage in push down. It needs to understand cost model for per operator. And lately, like the paper that Google published on C of accelerator, they more and more realize that the in-CPU and off-CPU accelerator need to cooperate in pipeline fashion much more tightly and with dependency exposed. So you have built many such systems yourself. Where do you see the frontier is actually in this kind of core design? Because database is well understood. What about the rest of it?
Yeah, so again, one guy says, if you don't talk about AI, nobody going to pay attention to you. But actually, I'm working on the AI domain and how to solve the problem more efficiently. Actually, these days, the large language model is it compute problem or a memory problem? It's actually memory problem. Then if you want to solve the problem efficiently, how you want to design your system and the actual accelerator all together, that is very important. So that's why we have AI software hardware co-design workstream in the OCP. But as I dig into that problem, actually, especially the large language model kind of application, since the existing solution cannot address problem properly, how to solve the problem more efficiently is really need co-design approach. Otherwise, you just build the accelerator agnostically, which actually introduces a lot of inefficiency when you're processing. Yeah. Okay.
Yes. It's obviously co-design is very important, but I would say beyond co-designing, we should do the software-driven design. So in order to not breaking existing software platform, also all the pain points and benefits should be seen, should be visible and then obvious from software side, and then all the costs and the pain points from the software side should be addressable in XPUs and computational storage.
So I want to bring some bad news about co-design. I think it is essential. Unfortunately, gotten much worse, more difficult. As Pankaj said, in the past it used to be a hardware person and a system software person sat together and did something, and probably released them close together. So a hardware person talked to a database optimization person. That's not difficult. Now we're talking about the hardware person talking with an ML researcher, a statistician. The hardware person takes 3 years to deliver something. The statistician needs to compete at a few weeks increments, and there's a major gap there. So both in terms of what they understand and the speed at which they're working. So we have to start breaking down this problem and see if we can make progress. One thing that we have to figure out is, are there tools abstractions to at least get a common language between the two sides? Because right now we speak very different languages. We, or most of us, don't understand statistics, and they don't even know how the systems work, right? So we have a really hardcore design problem there.
No, I agree. I thought that these problems were hard in the HPC space, where you sort of have to bridge between domain scientists and hardware software people, but this is a completely different level. The hope is kind of looking outside of the AI domain, which is, yes, extremely, extremely rapidly evolving, but looking at some lessons learned of what has worked in other domains. So database example is a good example. Finding some intermediate representation layer that's reasonably captures a number of properties of a significant workload domain. We've seen this in databases, we've seen this in graph, we've seen this in other domains, and so kind of finding that kind of connecting point to facilitate co-design around a smaller set of primitives that can be helpful.
Data format. So one of the reasons we need to move data is because of this, right? If you don't have this problem, you may not need to move data that much. So let's talk about the data format. Yeah, Ada?
Hoshik. Okay, yeah. So I think so fragmentation, we mentioned earlier that fragmentation is also very important issues, and software programmability is very important, flexibility important. So to address these issues, open data format, open common interface specification is very important. So to facilitate this computational XPUs into system.
So I went to a talk earlier this week that talked about specifically floating point virtualization, right? But yes, yeah. So there may be two sides to this. Sort of on one side is kind of establishing formats and standards around data representations, but maybe there is another way that we can make progress by maybe abstracting some aspects of the data format at the application level, and then being able to more transparently integrate transformations or specialization depending on where and how data needs to be or how you want to process data because of some system constraints.
That's quite interesting comment.
So just one thing, obviously it's nice to have open formats, but a related point is that a lot of the overheads that we have in systems, they have to do with translating between formats open or not. And one of the reasons that we cannot easily optimize that there is no end-to-end view of all the pre-processing and processing I need to do. These words are totally separate. And sometimes if you could see the problem end-to-end, you could see like, oh, I'm doing sampling at the end of this thing. So why am I translating all the data early on? I wouldn't do sampling, push it earlier. And having some way of also viewing computation end-to-end may help us reduce the overheads of some amount of translation between formats that may be still necessary.
I think ultimately our friend in computing is math. This is 50-year-old success story in computer science. So now faced with problems that are dominated by vectors and graphs, these are concepts that have very good definition in math. They mean the same operations on graph, like shortest path, or operations on vector, like horizontal and vertical operations. They mean the same thing. So Apache Foundation began the Arrow effort to capture a few common formats, and they're doing very well with vectors, and they're struggling with graphs, in my opinion. And they're even starting to attack compute. Sometimes just expression trees, sometimes the simple things like vectors and dot products, addition and dot products. So I actually pin my hope on the success of this effort. I looked at most of the 1,000-page spec, and I learned so much from reading this. It looks like some really good people have put their heads together and trying to do the right thing, so we should help them and leverage their work. That's my view.
Okay,
yeah.
Thank you. So let's move to the last topic. So level abstraction. So it's about, okay, you can program at different level, as very low level, the device level, or very high level, service level, like the RESTful interface, but there are many things in between. So that is actually the problem related to the kind of ease of use and how you can make the implementation portable and work with other applications developed for other different devices, right? So can you share your opinion about it? So.
Maybe start with
Christos.
Yeah.
Let's say, I guess one interesting point to make here is that, look, we all operate at different levels of abstraction, so there's never going to be one level that satisfies everyone. So probably a good question is, how do you bridge between these levels of abstraction? How do you bridge basically the statistician's work to all the way to how the hardware person looks like? And there have been a few things in our community that has been successful. The roofline model was put together by hardware people. Okay, my advisor, my office mate at Berkeley, so I know them quite well. But it has been quite easy for statisticians to understand and wrap their head around it. Unfortunately, it's very narrow. Like it captures like one operation or one chip or one metric multiply unit. So maybe we need to extend it. How do you describe bigger systems, heterogeneous systems, more complicated systems at that level that can bridge the worlds between users and system builders?
Yeah.
Sort of finding the right level of abstraction is really going to close the debate on all of the previous points that you brought up around co-design and formats and everything else. So I do think that we are going to continue having multiple levels of abstractions, which really match the productivity of the domain scientists or engineers, right? But we'll have to put effort into translating among them.
I maybe want to add one point. I think in the age of software-defined infrastructure and vertical integration, it's going to be that there are going to be multiple abstractions at different points in time in the same system. In fact, if you have a controller endpoint, and you install a service on it like CUDA runtime, all of a sudden this can accept a CUDA library operation. You put a machine learning CUDA library operation, all of a sudden PyTorch has something that they can use. So I think we need to understand and realize that our optimizers and our schedulers, for example, need to take a view of the system that's not a fixed thing. It evolves under software definition and under workload. And it puts pressure on developing better optimization algorithm to develop a quick cost and workload model to target it, to get the work done, and have a new situation and deal with it in the next minute, I think.
Okay. As a device vendor and solution provider, I think about this all the time, and this is very challenging for me to find the right level of abstraction. So if I lower the level of abstraction to a more low-level functions, then it can be more primitive, or can be applicable to more general use cases. But the benefit of offloading will be diminished. Especially, it has to continuously work with the whole CPUs, and then it'll have an extra overhead. And then if we put a more higher level abstraction, then we can have a more benefit out of it. But it'll rely on and depend on to a certain application and certain use cases, which is lowering the market size, our market size. So finding the right level of abstraction is very challenging part for me.
Okay. So since you heard what we discuss, you may think, okay, so what are you going to do? And you have a lot of issue and open questions. So, where this actual work stream is heading for? So instead of diverging the discussion too much, actually I ask panelists, okay, give me some hope. So so it's a really different format of the typical panel discussion. So I'd like to ask each of the panelists to, okay, give me some hope, the technological hope, to we can actually address this problem, not just diverging discussion all over the place, right? Okay. Next.
So one thing that we've seen is very helpful in domain-specific context is making the investment in understanding characterizing the workload and understanding the benefits that a specific device technology can provide for that workload. And so the process itself is challenging, but I think that it is challenging because from a device vendor, you have a lot of tools and APIs and microcode that you internally use, but then you don't export that. And then so from the system software stack, we kind of invent other ways to guesstimate what exactly is going on, both at the OS, application runtimes, and application level. And so kind of putting maybe more emphasis, sort of accepting the fact that we're not going to have a device be ideal for every possible application at every possible point of time, and just making it possible to support the decision-making that can go in the process to optimize around different metrics, around different policies. That, I think, is doable and can be quite effective, can go a long way.
Okay, so it's Hoshik, since you are one of the device vendor, you may have some comment about it, right?
Well, yeah, I'll pass this topic.
Okay.
Yeah.
All right, so we talked about some difficult problems, and they sound quite impossible. But hey, we're engineers. What do? We break it down and we start making progress, right? So let's talk about you try to optimize systems. What can you do? One thing that at least my students and I learn the painful way is that start from the very beginning, separating the control plane from data plane, like from the very, very beginning. And this makes sense for the following reason. The data plane, you throw acceleration, okay? Whatever it is, compute, data movement, whatever, like you throw your favorite accelerator there, you get something. And control plane is where you will engineer flexibility. And by separating the two, you don't have to compromise between the two. And actually, in the control plane, you can start taking profiles. You don't have to do, just old-fashioned profile-driven optimization. Throw your favorite machine learning, reinforcement learning algorithm. It will probably tune something better than you could think alone. The second thing that's kind of interesting is that we'll always struggle between compatibility and being able to innovate. And some of us, myself included, spent quite some time trying to take things out of operating systems and do them on the side. And we've kind of learned that probably that's not a great idea. If you separate controller from data plane, the OS is a compatibility layer, and you can customize it as well. If you look at eBPF and a bunch of other things we did in research, they allow you to customize the policy in the OS, and it can work fine. You can have your Pi and ET2 between a very well-running, efficient system and a very compatible system. And then the thing that everybody has been saying here, hey, look, we may not know exactly how to build one device for all the patterns, but if we build a system that has sufficiently different devices, we can synthesize the group of resources that your application really needed. Like, if you want a specific ratio of flops to gigabytes per second, which no device gives you, that's okay. We'll find some combination of device that gives it to you. The catch, of course, is that we need to build a very capable network between them. And we can have a long discussion about hardware and software issues there. And I'm going to pause here. I want to tell a few things about the co-design with applications, but it's a different topic. So if somebody wants to push back on me and disagree, that'd be great.
Yes, this is related to co-design. I agree, but the reason I passed to answer this question was this was supposed to be a technical hope, right? But from a device vendor, yeah. I mean, we as a device vendor, our focus scope should be limited to the device level. We want to move beyond device. We want to go beyond the device and go to the system level. But many system players are not allowing us to do that, right? So we are quite limited. But with device level optimization, we see a limitation. But so that is actually a problem. So even though we want to do more than that, so sometimes we have to negotiate with system designers. And then if we go higher, as I said earlier, it's also related to that level of abstraction, right? So it's go higher, so the market is being limited, and then we will be dictated by certain customers. So that's the problem.
Okay.
Oh,
as a
okay,
hope.
Okay, all right. Hope. Oh, this is hope. So, yeah. To enable and to facilitate this kind of XPUs and computational memory and storage and everything. So we better. I think as a device vendor, I like to see one successful success story, and I like to enable one working scenario. So data analytics acceleration is, I think, one of the most promising key application for this data-centric computing. So we are focusing on data analytics acceleration for both computational memory and computational storage side. So to do that, we also need to pay attention and align with existing software ecosystem trends. And the trend is they are all supporting open data format for like Apache Arrow and a common interface specification like substrate to describe data compute operation in different layers of softwares. So this supporting this open format is, I think, very important. And but Christos also mentioned that translating for the open format, the common data format is also overhead, can be overhead. So here comes I think hardware software co-design. We have to when we design hardware, we have to consider this open format from the beginning. So as to make it less overhead in order to avoid this format translation. Yes, that's one thing. And then also, in order to enable and facilitate this offloading at different layers of software and different layers of engine, so sometimes I want to offload some function at the compute node, and sometimes I want to offload to computation memory, sometimes to DPUs, storages. We should have a common data view, so same data view, common data view. I think objectives can be functioning as this common data view with metadata, which helps analytics and statics information, some index information. We can achieve this with objects. So that's why I'm also working with partners to enable this object-based system in our computational storage and everywhere.
Okay.
Maybe I want to add to his message of hope. I think these open formats were invented not for us, but for all these thousands of applications that don't know how to work together. So the message of hope is that you might think that we are talking about future, but this happened independent of us, and they're already CPU, GPU learn to work together, and they don't want to copy vector when it moves twice. So they invent a common format called Arrow, And it's both communication format and memory format, so we can make it in the storage interface as well. And then same thing. So I think this next idea, right, because these are coming from the data side, and I wanted to give you an example from the 90s to tell you how much confidence we should have in this technology. So when I was at Tandem, and yes, Christos, we were in vertical setting where we had hardware and software, but we had to figure this out for hard disks in the 90s, how to operate computation on the other side of the I/O fabric near the I/O device. And so we knew how to make SQL, which has the best algebra and math for optimization. And for 40 years, this foundation has worked across relational database, non-relational database, Spark. Everything uses their open optimizer like Calcite. And now, like previous slide showed, there is even substrate format for carrying plan. So every year, they solve more problem. And I think the message of hope is that we have a huge foundation to leverage in this area. And so it's very promising technology that we can build on. And all big data problems turn into database problem that community is very embracing. And it gives us good answer based in math that we can use reliably.
Okay. Are you going to cover this one or not?
I mean, the other thing I think is that also without computational storage and computational memory in the room, since 2006 at least, all big company like Amazon write their application as tens of thousands of microservices. Mm-hmm. So I think the abstraction to wrap a service, to have container around it, is good, nicely maturing abstraction. Scott Shadley in one of the talks today talked about his experience at NGD. And there is good learnings in the industry. One of the problems that the previous Hynix people pointed out is that there is problem with virtual addresses, especially virtual addresses that can go across regions and devices. So in my startup, we try to help with that problem. We wrote a very nice paper that has 8,000 downloads in ACMQ. You can read it on how we are trying to help this area, so that you can just point to data instead of copying this around in traditional RPC. So I think in small way, embracing the big, powerful, well-embraced abstraction, and then building on that in computational memory, computational storage is good opportunity.
Maybe one message of hope as well is that there is a lot of inter-system problems which are essential to solve, a lot of good ideas, and we'll be busy for a while. I don't see us being replaced by ChatGPT anytime soon, so that's a message of hope. So hard problems and interesting ideas is the bread and butter of this community. So I'm hopeful.
Mm-hmm. Okay, great. Thank you for the great opinion. So the data-centric computing workstream basically not try to create something new from the scratch. That's not the goal. I believe there are a lot of technology we can leverage. And as you observed today, technology are there, how we can coordinate that and have a kind of consensus, kind of agreement with something, that is missing part, I think. So I actually proposed this workstream. We already have how we can actually enable data should be placed where the data processing can be done efficiently. Doesn't matter where, doesn't matter what. Once you identify that, that is the place, not just CPU, not just GPU, not just DPU, doesn't matter. If you can agree that, then I think we can come up with a reasonable solution through this kind of discussion.
Yeah.
So thank you for attending the panel discussion today, and especially thank all the panelists joined today from East Coast and somebody I lost for a long time. Thank you again, and big applause to the panelists.
Thank you for doing this.
Thank you.